Hey, hey, Dylan, Bradley, how are you doing? Rachel, Re- Regiana, I'm good, good. I got my mom back to her place in Adrian, about an hour and 15 minutes away, and then because my brother, he was out of town, went to um, uh, Colorado, and he's my brother is hey louder. My brother is a harmonica player. I don't know if you guys have heard of Eminem, but he played his harmonica for Eminem on a album, a cut of called Purple Pill. Anybody heard of that at all? I haven't heard of it. I did listen to it. Kind of a strange song, but so he went away to play with other people, but he got altitude six. Oh, okay, strange song. And they usually cut out the end. At the end, there's a minute of harmonica solo. They usually cut that out when they play it on the radio. So, but he got altitude sick. He could not play for the life of him. He said it was terrible. He needed oxygen. Um, so he came home and he's his car's not working, so we had to give him another car to use. And then we helped my mom get her because she's 92. Got some groceries for her and got her all set up so she can make it through the week because my brother does that stuff. It isn't. He said he wasn't prepared for it. He said, "Oh my gosh, try to blow into him to a harmonica and go." Ugh. It's like he was winded. He felt like he was an old man. Now he is an old man, but not as old as me. So I'm the older man. I'm the older, bigger brother. And again, he has a lot of resentments about that. I don't get it. Why does he have resentments? I didn't share with him. I was not a good brother. Hate to say, wasn't a good brother. Now remember this: when as you get older, your brothers and sisters, be nice to them because when they get old, they get big and they get mean. Whoa, he's not mean to me, but anyway, so good to see you guys. Let's see, we got DeAndre. How are you? And let's see, Adriana. Good to see you. Bryce. Good to see you. That's terrible. That's terrible. Hey, Isabella. Bella. How are you? Jasmine. John. Good morning. Let's see, Mackenzie. Good morning. Let's see any new people in here. Michaela. Natalia. Noah. Rachel. Riker. I got any new people? I had a bunch of new people in here. Grace, both Graces are here. Dalton. No, I don't see any new people. Bradley was the only new person. He was here last week. So Bradley's still new. You're Bradley, you're still new. Still new. All right, so we're going to be talking about the history of the atom, and it is a lot of information. So we're going to do it with a video because it gets pretty. There's a lot to read, and it would take like 45 minutes to do that. So I'd rather not do that. So what we're going to do is we're going to work in teams, and I'm going to give you this. Okay, I'm going to show it to you first. Let me do that. Show the entire screen, give you some music so you can hear it. And okay, so this is what we're doing. We're going to do a quizzes. Let's join the teams here. We got 26 people. We should be able to get enough people. Hey, Gabrielle. Gabby, how are you? Here we go. Click on that. You can join late if you join late. Here you go, and it's starting. Go ahead and get started on there. I'm going to turn my face off because I'm turning my head back and forth and it drive you crazy. All right, so British bunnies against the lazy squirrels. Right, so pick a team. I think it doesn't matter if they're full or not. Two participants. Okay, so it's just Chloe against Chloe. So if you could put your first and last initial, that way I get know who is. So I give you participation points, right? Participation points. I appreciate it. Thanks so much. All right. Thanks so much. DeAndre, Hatfield, Gabby, Grace T, and Grace N. I got both Graces. All right. And Loader, because you're LL, right? Loader L. So it just makes it easier for me to put that on there. Anybody else? 10 out of 20, 29. We should get at least half. Let's see if we can get 15. 15. Lazy squirrels to the win. Let's do that, lazy squirrels. That doesn't seem right. Lazy squirrels probably they're looking for food. They like my squirrel. They like my bird feeder. All right. Let's see. Is that it? 10 people. I see. Okay. Come on, Paris. Come on, Riker. Come on, Natalia. We got both Chloe's in there. We got both Graces. Isaiah, come on, let's go in there. Dylan, Dalton, Christian, Carmen. We're getting close. 12. We got to get like 3 more people to get halfway. Let's get 3 more people. Let's get 3 more people. Come on, Carly, Bryce, Bradley. Is Bradley in there? Yeah, Bradley's already in there. Adriana, are you in there? Adriana. All right, we're going to get started. We didn't get half. Okay. Didn't get half. Let's start this game. I'm going to close the chat, so if you come in late, you can see the quizzes thing here. Quizzes, if you can get in there, you can get in late. British Bunny's off to a right start, 1,200 points. Oh gosh, you guys are neck and neck. 1,800 for Lazy Squirrels. Pretty good. Lazy squirrels are not lazy. guys are really good. 71% blast accuracy. Pretty good. Almost done. Thanks, Rachel, for being that cheerleader. All right. We're going to end this game. Looks like the lazy squirrels are not lazy after all. All right. Chloe, Loader, Gabby, good job, guys. Okay. So, I'm going to we're going to do this video um, on the history of the copy link. Let's copy link. Okay. History of the atom. Okay. And I'm going to click out, put this on here, Control V. So it's much easier to watch this than to listen to me just talk on and on about for the next 45 minutes. This is like 9 minutes. So much easier to do. All right, so let me put this in the shared notes if anybody doesn't get it. All right, let me see if did I even link it? Nope, I did not even click it. There we go. Okay, so if you can get in there, ladies and gentlemen, I'm going to play this on this device. And let me go continue. All right, so we got to start all over again. Okay. This is a crash course. All right, let me know if you get in there. I got 0 people, 1 person. Let's see if we can get, we got 32. Let's see if we can get 16 people in there. 16 people counts as your participation point, goes towards your benefits, bonuses. Okay, remember, ladies and gentlemen, bonuses. It's not required to do bonus. If you don't do it, it does help your grade at the end of every 9 weeks. It goes up 50 points, but the bonuses get locked. They have to be done in a certain amount of time. So make sure that if you, I cannot open them. Because I have to open it for everybody, and got just those time limits. Remember the W5 assignments, W5 assignment 1, W5 assignment 2, we do in class. You are available, or you are the one that does W5, the quiz. So we do those assignments in class. Okay, so we got 12 people, almost 16. All
How do
right.
you picture an atom in your mind? Like this, or maybe one of these? If you understand enough about atoms to visualize any of those things, then you know more about atomic theory than the scientists did just 100 years ago. And like way more than.
All right. So this is, I got this in the wrong position. So let me see if I can show this to
Than they
you.
thought they knew 2,500 years ago. That's when Greek philosopher Leucippus and his pupil Democritus first came up with the idea that matter is composed of tiny particles. No one knows how they developed this concept, but they didn't think the particles were particularly special. They just thought that if you cut something in half enough times, eventually you'll reach a particle that can't be cut anymore. They gave these particles the name atomos. Theory than scientists did just 100 years
so
ago.
I had to go
and
ahead
like
so
way
you can
more
see what was that? Okay. Indivisible, right? Indivisible. They're uncuttable, indivisible. Right? So 13 people. Good job, guys. We got all but maybe one or two. And again, 14. We're almost halfway there. You guys are doing great. All right, so we got just one person.
Than they thought they knew
maybe a laggy
2,500 years
computer.
ago. That's when Greek philosopher Leucippus and his pupil Democritus first came up with the idea that matter is composed of tiny particles. No one knows how they developed this concept, but they didn't think the particles were particularly special. They just thought that if you cut something in half enough times, eventually you'll reach a particle that can't be cut anymore. They gave these particles the name atomos, which means uncuttable or indivisible. So basically they thought that iron was made up of iron particles and clay was made up of clay particles and cheese was made up of cheese particles. And they attributed properties of each substance to the forms of the atoms. So they thought that iron atoms were hard and stuck together with hooks. Clay atoms were softer and attached by ball and socket joints that made them flexible. And cheese atoms were squishy and delicious. Now this makes a certain amount of sense if you don't happen to have access to electron microscopes or cathode ray tubes or the work of generations of previous scientists. Because the fact is, atomic theory as we know it today is the product of hundreds, if not thousands, of different insights. Some models, like that of Leucippus, were just blind guesses. As time went on, many more were the result of rigorous experimentation. But, as has been the case in all science, each scientist built on what had been learned before. We've been talking a lot about the fine.
All right. Each scientist builds on the work of previous scientists or nothing. What is it? They start from scratch. It's kind of like what we do with making food. You know, I look at a recipe and I start from there. I don't create my own recipes. I just do what I can do with that. And most of you said the work of previous of others. Yeah, and that's what we did. Think about it. 2,300 years ago, they came up with this idea, and then it's just the last 200 years that we've been able to decide what these things are. All right, we still had just one person not responding.
Details of chemistry in recent weeks, and we're going to keep doing that as we move on to nuclear chemistry and then to the basics of organic chemistry. But before we do, I wanted to set aside some time to explain how we know what we know about the atom today and how we know that we're not quite done figuring it out.
That's why we need you, ladies and gentlemen. You've got to be our next scientist and chemist and mechanical engineer.
I think that once Leucippus and Democritus came up with the general idea of atoms, it'd be pretty easy for someone else to take that little indivisible ball and run with it. But you'd be wrong. The next major developments in atomic theory didn't come along for nearly 2,300 years. I've already told you, for instance, about the French chemist Antoine Lavoisier, who proposed the law of conservation of mass, which states that even if matter changes shape or form, its mass stays the same.
All right, so the father of chemistry is the person who came up with the law of conservation of mass. Anybody get it? Anybody get it? Let's see if you did. Yes, somebody got it. Antoine Lavoisier, father of chemistry. Cool, you guys got it. Father of chemistry. Got less people there. Father of chemistry, letter C, letter C. See if it's letter C. Good job. One person, one person has a laggy computer. I'm not sure.
And you should remember the English teacher James Dalton, who determined that elements exist as discrete packets of matter. Thanks to these and other great minds by the 1800s, we had a better grip on the general behavior of atoms. The next logical question was, Why? Why do they behave the way they do? This led to the investigation of atomic structure. In the 1870s, scientists began probing what stuff was made of using discharge tubes, basically gas-filled tubes with electrodes at each end, which emit light when an electrical current passes through them. Basically what a neon light is. Because this light was originally produced by a negative electrode, or cathode, it was called a cathode ray, and it had a negative charge. But in 1886, German physicist Eugen Goldstein found that the tubes also emitted light from the positive electrode, basically a ray heading in the opposite direction, which meant that there must also be a positive charge in matter. Goldstein didn't fully understand what he'd discovered here. I mean, scientists still hadn't figured out what was responsible for the negative charge in the rays either. Then, English physicist J.J. Thomson took the discharge tube research further. By measuring how much heat the cathode rays generated, how much they could be bent by magnets, and other things, he was able to estimate the mass of the rays. And the mass was about 1,000 times lighter than hydrogen, the smallest bit of matter known at the time. He concluded that the cathode rays weren't rays or waves at all, but were in fact very light, very small, negatively charged particles. He called them corpuscles. We call them electrons. So even though we
All right. Each particle of the atom has mass. Electrons are how many times lighter? I don't think he said, but it's 1,000 times lighter than the proton. Electrons. He discovered the electron. It's 1,000 times lighter. So letter A, 1,000 times lighter. Letter A. So if you put letter B, put 1,000 in there. Letter B is not correct. Letter A is a. So it takes 2,000 electrons to equal. There you go. 2,000 electrons to equal 1 proton. So it's 1,000 times lighter. Okay, good job. We just got that 14. And
we didn't understand what shapes they took. We knew that there were both negative and positive components to matter. The next question was, how were they arranged in the atom? Thomson knew that the atom overall had a neutral charge, so he imagined.
All right, what did Thomson know about the atom? It had a positive charge, had a neutral charge. Yay! Yeah, you did it. B, it had a neutral charge. Same number of protons as electron. Not letter A, letter B, letter B. Let's do letter B. There you go. Neutral charge. It had a neutral charge. All right, so he figured that out probably with a cathode ray tube. So 14. Okay, let's go.
Imagine that the negatively charged electrons must be distributed randomly in a positively charged matrix. And the very English Thomson visualized this model as a familiar English dessert. Plum pudding, the positive matrix being the cake, and the electrons the random floating bits of fruit within it. Even today, Thomson's model of the atom continues to be called the plum pudding model. And while a single electron's motion is random, the overall distribution of them is not. The next big step was taken by New Zealander Ernest Rutherford in 1909. He designed an experiment using an extremely thin sheet of gold foil and a screen coated with zinc sulfide. He bombarded the foil with alpha particles, which he didn't really know what they were, just that they were produced by the decay of radium. They were positively charged and they were really, really small. He expected them to just fly right through the foil with no deflection, and many of them did just that. But as it turned out, some of the particles were deflected at large angles.
All right, who developed the gold foil experiment? Democritus, J.J. Thomson, John Dalton, Ernest Rutherford. Ernest Rutherford, you got it! Ernest Rutherford. Almost filled it all the way around. Cool, cool, cool.
And sometimes almost straight backward. The only explanation for this was that the entire positive charge in an atom, the charge that would repel an alpha particle, must be concentrated in a very small area. An area that he called the nucleus. Because most of the alpha particles pass right through the atoms undeterred, Rutherford concluded that most of the atom is empty space. And he was correct. Rutherford would later discover that if he bombarded nitrogen with alpha particles, it created a bunch of hydrogen ions. Now, he correctly surmised that these tiny positively charged.
All right, Rutherford's experiment led us to believe most of the atom is empty space, or the atom has a negative core. Yeah, mostly empty space, and the atom has a positive core because they did an alpha particle, which was also positive. Right? And that's why it was deflected. So mostly empty space. So there's a lot of space there, even though it's kind of tiny. All right, we got almost everybody that we got here. We got one more person. and we get to 14%, but it's, sometimes you get to where you can't even press the button because there we go, because the
charged ions were themselves fundamental particles. Protons. Now we're getting close to reality. So these chemists had a fairly good idea of the structure of the atom. They just needed to figure out what exactly the electrons were doing. Enter Niels Bohr. In 1911, the same year the results of Rutherford's gold foil experiment were published, Bohr traveled to England to study with Rutherford. And as a physicist, he was also interested in the mathematical model set forth by German physicists Max Planck and Albert Einstein to explain the behavior of electromagnetic energy. Over time, Bohr came to realize that these mathematical principles could be applied to Rutherford's atomic model. His analysis of the gold foil experiment, calculations based on the proportion of alpha particles that went straight through, those that were slightly deflected, and those that bounced almost completely backward, allowed him to predict the most likely positions of electrons within the atom. Bohr's resulting model, sometimes called the planetary model, is still familiar to most people, probably including you. It represents...
All right, what type of model is this? Is this the electron cloud model, the atomic model, or the Bohr model, or the plum pudding model? Hey, you guys got it. Letter C, it's the Bohr model. Looks like a planetary model. Yeah, it looks like it's got a nucleus, which is the sun, and then everything orbits it, right? It's not correct, but it's the easiest one to visualize.
Represents the electrons in orbits around a small central nucleus. Each orbit can have a specific number of electrons, which correlates to the energy levels and orbitals in the modern model of an atom. And while it's definitely flawed, Bohr's model is very close to reality in some important ways. But like everyone I've mentioned in the past couple of minutes, Bohr was at once fantastically right and way off. The problem was those pesky electrons. It was the German theoretical physicist Werner Heisenberg who got everyone to understand just how huge and mind-blowing this electron problem was. But he was also the one who helped tie the whole mess up into a neat little bundle. Using his wicked math chops, Heisenberg discovered that it is impossible to know with certainty both the momentum of an electron, or any subatomic particle, and its exact position. And the more you know about one of those two variables, the harder it gets to measure the other one. So if you can't measure the position or momentum of an electron, you obviously can't say with certainty that the electrons in an atom are all neatly aligned in circular orbits. So he and a new wave of physicists and chemists proposed a new theory, a quantum theory, which proposes that electrons weren't particles or waves. Instead, they had properties of both and neither. By this thinking, the arrangement of electrons around a nucleus could only be described in terms of probability. In other words, there are certain regions where an electron is much more likely to be found. We call these regions orbitals. You know, the very same orbitals that you and I have been talking about. The ones that go by the names S and P and D and F and that form sigma and pi bonds. Those are the things that Heisenberg's theory predicts, and that's the modern understanding of atoms. Because it's based on probability, quantum-style atoms are often drawn as clouds with the intensity of color representing not individual electrons, but the probability of finding an electron in any particular position. For this reason, the quantum model is often called the cloud model of the atom. And now you know!
All right, electrons don't go around the nucleus round circular paths, but found in regions called electron clouds, proton clouds, neutron orbits. They are actually located in the nucleus. Oh, there you go. You got it. Letter A. Somebody misclicked. They're not proton clouds. They're electron clouds. Letter A. There we go. Everybody's got it. Yay. Yeah, electron clouds. You guys misclick.
All the people I've mentioned and many others put their heads together over time to build this current and, I might say, quite elegant understanding of atomic theory. Now, after 2,500 years, even though we can't see them, we can know what they're like and how they work because a long succession of scientists contributed bits and pieces to the whole fantastic picture. But it's also important to recognize that we still may not be quite all the way right. Thomson's contemporaries were sure that the plum pudding model was right. Scientists in Bohr's day fully believed that the planetary model was right. And today, we're extremely confident that the quantum model is correct. But it may not be all the way correct, and that's where you come in. The only way we can go on being sure is to keep asking questions and conducting experiments, and that's why you're taking chemistry and physics. Pay attention. Thank you for watching this episode of Crash Course Chemistry. If you paid attention, you learned that Leucippus and Democritus originated the idea of atoms nearly 2,500 years ago, but that the real work didn't really begin until both protons and electrons were discovered by experimenting with discharge tubes, and how Ernest Rutherford figured out what and where the nucleus is. You also learn that chemistry can sometimes be done with just math, like how Bohr figured out his model or the way that Heisenberg used math to usher in the quantum theory of the atom. This episode was written by Edie Gonzalez and edited by Blake.
All right. Who used the plum pudding model to describe the atom? J.J. Thomson, Democritus, Ernest Rutherford. Nope, it was J.J. Thomson. Yay! Everybody got it except for one. Come on, there you go. You changed it. Excellent, excellent, excellent. All right. And we just got, okay, so we are done there. Okay, so what I want to show you guys, as long as we're done here. Okay, so in your, all right, because there is an awful lot of material to talk about for the atom and all the people. So it's important that you look at your notes. Okay, so what I've done, and most people said something in first hour, Mr. Barnes had 111 slides. So I tried to pare them down. So in the module, right, there is, if I look at this correctly, week 5, let's go to week 5, week 5, there we go. Week 5 says atomic structure notes. All right, so up there is all the slides. This is the notes. If you click on this, and then you click on that, and I downloaded it. Oh, there we go. All right, so I have the slides. The important ones, I should take a few of them out. How to do the atomic number, the proton. I got some questions in there. But here are the ones that talk about the scientists. So what we're going to do is we're going to work on W5 assignment 2. So let's do that. Let's go over here, click on courses, and I'll give you that link so that you can, there we go. All right, let's go to courses, physical science, block 2. All right, so in the modules. Okay, so if you're looking in the modules, you have, wait for it, week 5. All right, so this is W5 assignment 2. Now remember, yesterday's bonus assignment is due September 27th. Okay, so I gave you a week. The basic, let's see, the periodic table bonus pretest closed yesterday, so I can't open that up anymore. So that is okay, but you do have the W5B post test that's open for a couple till tomorrow. So you can take that as many times, 3 times to get your 5 points, just to review. So bonuses don't have to be done. They are not. If you want bonus points, all these other assignments are still open till January 12th. So let's do bonus. Let's do this assignment. This is the assignment that counts, 15 points. All right, let's do this as a preview. I will give you the link. Tell me if you get in there, and we'll work on this together. Okay, so here is the link. All right, did I hit it? Click. There we go. Tell me if you got in there. All right, so I'm going to close this down to small, and I'm going to close this here, and I'm going to do the atomic structure there. So again, my suggestion to you when you take the quiz, because I don't help you on the quiz, is that you use these notes. All right, use these notes. Tell me if you got in there so I know that I'm not the only one talking or doing something. Okay. Hi, thanks, Chloe. All right, so if you guys will answer some questions for me, I will try to find them for you as well. Okay. Who is the scientist that first composed the idea of atoms? Okay, the first person to produce the idea of atoms was, who was it? Please don't put A, B, C, or D. Put the name there because it does change and it does. Thanks, Rachel. Thanks, Chloe. Yeah, it's Democritus. And you'll notice it's right there in the notes. Okay, lots of notes. That's the whole idea here. If an atom is combined with two to form molecules, what's the ratio? I think Dalton did this. So if you look with James Dalton, you have a lot of people, Lavoisier, solid ball theory for Dalton. All right, so all atoms of a given chemical element are identical. All matter's composed. And he says the law of atoms combine to form molecules. The ratio of atoms is constant. All right. So, the ratio. So there is two elements can combine to a compound. Then the ratio of the second element combined with the first element is always the ratio of the small. So which is what assignment? Okay, it's right here, Chloe. There you go. Thanks. So basically he's saying here, if atoms are combined to form molecules, the ratio of those elements, the ratio of the elements will stay what? Remain the same, are different, or can be different, same or different. Yeah, they remain the same, right? They do. So water, H2O, stays as H2O. It doesn't decide to be H3O, and that's water. You can make an H3O, but um, it's not easily done. Okay, which way did the stream of electrons curve toward the Thomson cathode? So let's take a look at Thomson. Here's Thomson. Here's his cathode ray, a little more. Now notice what the beam did. Which way does it bend toward? Yeah, curve toward the positive plate. So it was negatively charged and it was attracted to the positive, right? Number 4, which subatomic particle is referred to as the raisin in the plum pudding model? Let's see. Oh, here we go. J.J. Thomson. Oh, there you go, Chloe. It says right here, Thomson's plum pudding model is a positive charged sphere and negatively charged, like the raisins, the electrons. Number 5. True or false, Dalton postulates still hold up today? And I think we said, let's see, Dalton, I think we thought this was true. All matters composed, all atoms are different. Okay. Dalton was credited with 3 atomic laws that were proven after time. His ideas are so brilliant, even today, they're essentially intact, roughly unchanged. So we're going to say true on this one or false. All Dalton postulates still hold up in today's scientific theories. Roughly unchanged, except for slightly corrected. So I think we're gonna say true. Is that okay? Are we gonna try to do that one? True on this one. All right, let's double check here. Nope, that you're right. It is false. False. Yep, you're right. It is false. True or false? Number 6. All atoms of different atoms are completely different from one another. All atoms of different atoms are completely different from another. What did we say there? That one is true. Okay. How did you guys do? Anybody need to see the answers again? Anybody need to go over them? Good. Thanks, Chloe. Anybody missing? Unless any one of these. I'll go back if you'd like. Okay, nobody's saying anything. So let me let you guys know that I think it was Chloe was saying that if you join my YouTube channel, okay, and you look at my videos, right? You'll notice that here is W5 assignment 1, the atom structure, which we did on Tuesday. We did that on Tuesday. It's a 5-minute video that I cut out from of the conference videos. There is week 5 atomic atom practice. I'm going to be doing this more often because I can link this to everybody's video rather than having a conference video for everybody. There is the FET build an atom instructions here. There's W3 assignment 1. That was 5 minutes. W4 assignment 2, W2 assignment 2, W2 assignment 1, W3 assignment 2, W4 assignment 1. And here's W1 assignment 1, but you don't have to do that one. That one those are bonus assignments. So I've got all these assignments here for you. I will be putting W5 assignment 1, assignment 2 in this. So